Open addressing is a way to resolve collisions in a hash table by keeping all entries inside the table itself. When a new key hashes to a slot that is already occupied, we do not store the key in a separate linked list as in chaining. Instead, we look for another free slot by following a probe sequence that depends only on the original hash value, and on the method, we choose linear, quadratic, double hash, etc. Analogy: think of a row of parking spaces, the table. When a car arrives, a key and its assigned space is taken, the driver walks forward looking for the next empty spot. The rule that tells the driver where to look next is the probing function. All cars stay in the same row, there is no separate side street, no extra structures. The essential principle is: compute a primary hash h of k that maps the key k to an index in 0 to m-1. M equals table size. If slot h of k is free, store the key there. If not, generate a sequence of alternative indices I0, I1, I2, and so on using a probing function f of I, k, and try each in turn until a free slot is found or we have examined the whole table. Search and delete follow the same sequence, stopping when the key is found or an empty slot that has never been filled is encountered. Open addressing works only when the table is not completely full, otherwise, the probe sequence would never find an empty slot. Explanation: linear probing. Probing function I sub j equals h of k plus j modulo m for j equals 0, 1, 2, and so on. The next slot is simply the one immediately to the right, wrapping around. In the parking lot analogy, the driver moves one space forward each step. Primary clustering: because every key that collides follows the same linear path, groups of occupied slots tend to stick together, forming a cluster. New keys that hash anywhere inside the cluster must walk through the entire cluster, making the cluster grow like a snowball. Mathematical analysis: let alpha equals n divided by m be the load factor, where n is the number of stored keys. Assume simple uniform hashing, that is, each key's initial slot is equally likely. The expected number of probes for an unsuccessful search is E sub unsuck equals 1/2 times open parenthesis 1 plus 1 over open parenthesis 1 minus alpha close parenthesis equals 1/2 times open parenthesis 2 minus alpha divided by 1 minus alpha close parenthesis. For a successful search, the expected number of probes is E sub suck equals 1/2 times open parenthesis 1 plus 1 over open parenthesis 1 minus alpha close parenthesis equals 1/2 times open parenthesis 1 plus alpha divided by 1 minus alpha close parenthesis. These formulas come from summing a geometric series that models the probability that a probe lands in a filled slot. As alpha approaches 1, the expected probes blow up, showing why linear probing deteriorates quickly under high load. Example: with m equals 10 and n equals 4, alpha equals 0.4, the expected probes for a successful search are about E suck equals open parenthesis 1 plus 0.4 close parenthesis divided by open parenthesis 2 times open parenthesis 1 minus 0.4 close parenthesis equals 1.4 divided by 1.2, approximately 1.17, meaning most keys are found on the first or second try. Quadratic probings. Probing function I sub j equals open parenthesis h of k plus c1 times j plus c2 times j squared close parenthesis modulo m, where c1 and c2 are constants, often c1 equals c2 equals 1/2. The step size grows quadratically, so the driver jumps further each time. First step equals 1 slot, second step equals 3 slots ahead, third step equals 6 slots ahead, etc. Secondary clustering: two keys that hash to the same initial slot will follow the same quadratic sequence, but keys that start at different slots will have different sequences even if they later collide. This reduces clustering compared to linear probing, but a weaker form of clustering, secondary, still exists because the shape of the sequence is identical for all keys sharing the same start. Coverage guarantee: for a table size m that is a prime number and using c1 not equals 0, c2 not equals 0, the quadratic probe sequence will visit all slots before repeating if m is prime and c1 and c2 are chosen such that the quadratic polynomial is a permutation modulo m. A common safe choice is c1 equals c2 equals 1/2 and m prime. Then the sequence covers at most m over 2 slots, which is enough if we keep alpha less than 0.5. More formally, the set open brace open parenthesis C1 times J plus C2 times J squared close parenthesis modulo M vertical bar, J equals 0 to M minus 1 close brace, is a complete residue system when M is prime and C2 is not divisible by M. Example, let M equals 11, C1 equals C2 equals 1. For key K with H of K equals 3, the probe indices are 3, 4, 6, 9, 2, 7, 1, 8, 5, 0, 10. All 11 slots appear exactly once before the pattern repeats. Mathematical expectation. The expected number of probes for successful search with quadratic probing is roughly E suc approximately open parenthesis 1 divided by open parenthesis 1 minus alpha close parenthesis, when alpha is less than or equal to 0.5, which is slightly better than linear probing because clusters are smaller. Double hashing. Use a second hash function to compute the step size, making the probe sequence depend on the key in two independent ways. Construction of second hash: choose H2 of K such that 0 less than H2 of K less than M, and H2 of K is relatively prime to M. A common choice is H2 of K equals 1 plus K mod M minus 1 when M is prime. Probe sequence formula: I sub J equals H1 of K plus J times H2 of K modulo M for J equals 0, 1, 2, and so on, where H1 of K equals K modulo M is the primary hash. Avoidance of clustering: because the step size H2 of K varies with the key, two keys that collide at H1 will almost surely have different step sizes, leading to completely different probe paths. This eliminates both primary and secondary clustering. Coverage guarantee: if M is prime and H2 of K is non-zero modulo M, then H2 of K is automatically relatively prime to M. Consequently, the sequence H1 of K plus H2 of K, H1 of K plus 2 times H2 of K, and so on cycles through all M slots before repeating. Therefore, a free slot will always be found as long as the table is not full. Example: M equals 13, H1 of K equals K modulo 13, H2 of K equals 1 plus K modulo 12. For key K equals 27, H1 equals 1, H2 equals 1 plus 27 modulo 12 equals 1 plus 3 equals 4. Probe indices 1, 5, 9, 0, 4, 8, 12, 3, 7, 11, 2, 6, 10. All 13 slots appear. Expected probes: with uniform hashing. Double hashing behaves like a random probe sequence, giving the classic expected cost. E success equals open parenthesis 1 over alpha close parenthesis times natural log of 1 over open parenthesis 1 minus alpha close parenthesis, and E unsuccess equals 1 over open parenthesis 1 minus alpha close parenthesis. These are the best among open addressing methods. Note: the formulas above assume that the hash functions behave like random functions, an assumption called simple uniform hashing. The load factor alpha equals n/m measures how full the table is. N equals stored keys, M equals table size. All three operations, search, insert, delete, depend heavily on alpha. When probing, each examined slot is either occupied with probability alpha or empty with probability 1 minus alpha, simple uniform hashing. The number of probes needed is the length of a geometric random variable with success probability 1 minus alpha, finding an empty slot. E unsuc equals 1 divided by 1 minus alpha. Derivation: the probability that the first probe hits an empty slot is 1 minus alpha. If not, we try again, giving a geometric series. E equals sigma sub k greater or equal to 1 of k times alpha to the k minus 1 times 1 minus alpha equals 1 divided by 1 minus alpha. When the key is present, its position is equally likely among the n occupied slots. The expected number of probes equals the average position in the probe sequence. E suc equals 1 divided by alpha times natural log of 1 divided by 1 minus alpha for double hashing or random probing. E suc is approximately 1/2 times open parenthesis 1 plus 1 divided by 1 minus alpha close parenthesis for linear probing. E suc is approximately 1 divided by 1 minus alpha for quadratic probing, with alpha less than or equal to 0.5. These formulas show a steep rise as alpha approaches 1. For alpha equals 0.7, double hashing gives E suc approximately 1 divided by 0.7 times natural log of 1 divided by 0.3. About 1.43 times 1.2 equals 1.72 probes, while linear probing gives about E suc approximately open parenthesis 1 plus 0.7 close parenthesis divided by open parenthesis 2 times 0.3 close parenthesis equals 2.83 probes. Insertion is essentially an unsuccessful search for a free slot, then a write. Hence the expected cost equals E unsuck. Deletion itself is big O of 1 if we simply mark the slot, but the presence of tombstones can increase the effective alpha for future searches, raising the probe count. Practical rule of thumb: keep alpha less than or equal to 0.7 for linear probing, less than or equal to 0.5 for quadratic probing, and less than or equal to 0.9 for double hashing to retain constant time performance. Deletion handling with tombstones. In open addressing, we cannot simply clear a slot when deleting because a later search for a key that collided and was placed after the deleted slot would stop at the empty slot and incorrectly report not found. The solution is to place a tombstone, a special marker saying this slot used to hold a key. How it works is, when deleting KK, replace its entry with a tombstone value, the tombstone symbol. During search, treat a tombstone the same as an occupied slot. Continue probing until the key is found or a truly empty slot, never used, appears. During insertion, a tombstone slot is considered available. The algorithm may place the new key there, thereby reusing space. Effect on later operations. Tombstones increase the effective load factor because the probe sequence now sees more occupied slots, real keys plus tombstones. Let T be the number of tombstones. The effective load becomes N plus T divided by M. As T grows, average probe lengths rise according to the same formulas that use alpha, but with alpha replaced by N plus T divided by M. Periodic rehashing, building a fresh table and inserting only live keys, removes tombstones and restores the original load factor. Real-world analogies. Imagine a library shelf where some books are removed. Instead of pulling the book out and leaving an empty space that would mislead a patron looking for a later book, the librarian puts a placeholder card, a tombstone indicating book used to be here. New arrivals can be placed on that placeholder, but a patron still has to scan past the placeholder to know the shelf is still occupied. A cost summary. Deletion equals big O of 1, just mark. Subsequent searches and insertions see a slightly higher expected probe count proportional to N plus T divided by M. Rehashing optional costs big O of M, but is amortized over many operations. Comparative analysis of probing methods. Linear probing, primary clustering is high. Probe sequence predictability is fully deterministic. I plus J space overhead is none. Load factor limit is less than or equal to 0.7. Average successful probes is 1 plus alpha divided by 2 times 1 minus alpha. Quadratic probing, secondary clustering is medium. Probe sequence is deterministic but jumps grow quadratically. Space overhead is none. Load factor limit is less than or equal to 0.5 to guarantee full coverage. Average successful probes is approximately 1 divided by 1 minus alpha for alpha less than or equal to 0.5. Double hashing, primary clustering is none minimal. Probe sequence is pseudo-random depends on second hash. Space overhead is none but requires 2 hash functions. Load factor limit is less than or equal to 0.9, still near constant. Average successful probes is 1 over alpha times natural log of 1 over 1 minus alpha. Time-space trade-off. All three use the same table size, no extra pointers, so space overhead is identical except for storing a second hash function in double hashing, which is usually negligible. The real trade-off is runtime variability. Linear probing has the smallest constant factor per probe, just a simple index increment, but suffers from clustering, causing worst-case O of M behavior near full tables. Quadratic probing reduces clustering, but needs careful choice of constants and may not visit every slot if alpha greater than 0.5, leading to insertion failures. Double hashing offers the best average case behavior and near-perfect clustering avoidance, but each probe requires 2 hash calculations, slightly increasing per probe CPU time. Exam-style proof questions often ask you to: Number 1, prove that a given probing function f of I equals h1 of k plus I times h2 of k modulo m visits every slot when m is prime, and h2 of k is relatively prime to m. Number 2, derive the expected number of probes for linear probing using geometric series. Number 3, show that quadratic probing fails to guarantee full coverage when m is even. Typical strategy: start from the definition of the probe sequence, use modular arithmetic properties. For example, greatest common divisor of H2 and M equals 1 implies the multiples of H2 form a permutation modulo M, and then apply the uniform hashing assumption to turn counts into probabilities. Practical recommendation for students: memorize the 3 probe formulas, the clustering type each suffers from, and the key inequality for the load factor alpha. Being able to sketch a short proof of full coverage for double hashing earns you easy marks. Explanation: typical examination problems. 1. Design a probe function. Question: given a table size m equals 101 prime, design a double hash probing scheme. Provide h1 of k equals k modulo 101, h2 of k equals 1 plus k modulo 100. Probe I sub j equals open parenthesis h1 of k plus j times h2 of k close parenthesis modulo 101. Show that h2 of k is never a multiple of 101. Thus, greatest common divisor of h2 and 101 equals 1, which gives full coverage. 2. Compute expected probes. Question: for linear probing with load factor alpha equals 0.6, compute the expected number of probes for a successful search. Solution: use E suc equals open parenthesis 1 plus 1 divided by open parenthesis 1 minus alpha close parenthesis divided by 2. Plug in E equals open parenthesis 1 plus 1 divided by 0.4 close parenthesis divided by 2 equals open parenthesis 1 plus 2.5 close parenthesis divided by 2 equals 1.75 probes. 3. Select optimal strategy. Question: a hash table will store up to 900 items and has capacity 1024. Which open addressing method gives the lowest average probe cost? Justify with calculations. Work: load factor alpha equals 900 divided by 1024, approximately 0.879. Linear probing: E suc approximately open parenthesis 1 plus alpha close parenthesis divided by open parenthesis 2 times open parenthesis 1 minus alpha close parenthesis, which is approximately 1.879 divided by open parenthesis 2 times 0.121 close parenthesis, equals 7.76 probes. Quadratic probing with alpha greater than 0.5 is not safe, may not guarantee insertion. Double hashing: E suc approximately open parenthesis 1 divided by alpha close parenthesis times natural logarithm of open parenthesis 1 divided by open parenthesis 1 minus alpha close parenthesis, which is approximately 1 divided by 0.879 times natural logarithm of 1 divided by 0.121 equals 1.138 times 2.11 equals 2.40 probes. Conclusion: double hashing is optimal. 4. Proof of clustering avoidance. Question: explain why double hashing eliminates primary clustering using the concept of secondary hash independence. Answer: sketch. Primary clustering occurs when many keys share the same increment between successive probes. In double hashing, the increment equals h2 of k, which depends on the key. 2 keys with the same initial slot h1 of k will almost surely have different h2, so their probe sequences diverge after the first step. Hence, no long run of consecutive occupied slots is formed solely by the probing rule. Clustering is reduced to random collisions. 5. Tombstone effect. Question: after 200 deletions in a table of size 1000, initially 800 keys, what is the effective load factor and expected probes for an unsuccessful search using linear probing? Computation: real keys equal 600, tombstones equal 200, effective alpha equals open parenthesis 600 plus 200 close parenthesis divided by 1000 equals 0.8. Expected unsuccessful probes equals 1 divided by open parenthesis 1 minus alpha close parenthesis, which is 1 divided by 0.2 equals 5 probes. These sample problems illustrate the typical calculations and reasoning expected in exams. Final tip: practice converting the generic formulas into concrete numbers quickly. That is often the fastest way to earn marks on time-pressured tests.